I arrived yesterday, so I'm a bit frustrated because it seems that it was, and it still is, a nice place to be. I wish I had stayed more, and I wish I had more time to stay here. I have not attended John's lectures, so there might be some overlap. I went through the slides. It seems that there is not too much overlap, but in case there is, feel free to let me know and feel free to tell me, okay, John told everything about this, so don't bother. Or if there is something that you feel would be nice, I don't know, if John promised that I would talk about something, let me know as well. So this is intended to be somehow the extension of John's lectures, and I will go into more details about some specific aspects of learning theory. There will be 4 lectures. The first one will be about the union bound, which is one key ingredient of obtaining bounds in learning theory. And the second lecture will be about variance and local Rademacher averages. And this is the second key ingredient of statistical learning bounds. And then there will be some, so the 2 other lectures will be more about applying the bounds to specific situations. Lecture number 3 will be about loss functions and how to adapt the bounds that we will see in the first 2 lectures that will be restricted to the binary classification case to more generous setting, still in classification, but where the loss function is a convex loss function. And the 4th lecture will be some applications to SVM. I'm not sure we will be able to go all the way to the 4th one, to the end of the 4th lecture. I will try to adapt the level. So if there are something that are too easy or too difficult, again, feel free to interrupt me and let me know. So the plan for today is the following. I will first recall briefly what is the setting that we are dealing with. And again, I will focus on binary classification in the statistical learning theory framework. And I will recall you what is the union bound, a basic version of union bound, and then introduce more and more refinements about this union bound. Then another topic that we will talk about, and that explains the title, Pack Bayesian Techniques, is what is called randomized classification. And that's where these Pack Bayesian bounds occurred first. And then we'll see some other refinements. So it will be all about the union bound. Okay, so maybe I'll introduce the setting again and then tell you what is a union bound, because it may not be obvious for all of you. So the setting is quite classical. I don't know if this works. Okay. So we have an input space, X, and output space, Y. And here, as we are in classification setting, our output space has only 2 elements. It's +1 or -1. And the assumption that we make, or the model, or the way we model the problem, is that we assume that we have a pair of random variables, X and Y, that are, I don't know if this is very convenient. Maybe I should avoid it. So we have a pair of random variables. Maybe the mouse would do it. Can everybody see the mouse? Okay. So we have a pair X, Y, and okay, X belongs to our input space, which is anything, any space, and Y is either +1 or -1. And this pair is assumed to be distributed according to some distribution which we call P, which is unknown. And instead of knowing P, which would be ideal, we observe a sequence of N. N is the sample size, IID pairs, Xi, Yi, which are sampled according to this P. So we observe, we get knowledge about this unknown probability distribution via the observation of these pairs Xi, Yi. This is our training sample. And the goal is, as usual, to construct a function that allows to predict the output Y from the input X. And this function we call g, it's usually called a classifier in this setting. And it's for any instance x in the input space, it maps it to either +1 or -1. And it has to, I mean, the goal is to build a function such that it is able to predict the random variable y from the random variable x, which means, and we have to define what means predicting in this setting. And predicting means making as few mistakes as possible. And the way we measure the number of mistakes is via this formulation here. We call that the risk. And the risk is the probability that when we take a pair xy of random variables from this unknown p, and we try to predict y from x using this function g, we make a mistake, which means the predicted outcome is different from the one we observe. And this probability of making mistakes can be written as the expected value of the indicator function. So this one here with a subscript here is the indicator function that this is true. It takes value 1 when this is true and 0 when it's not true. And the expected value of such a function is nothing but the probability that the event is true. Okay, so this is a bit of notation, but it doesn't say anything complicated. It just says that we want to find a function that makes few mistakes. Now, of course, there are some issues, and which explain why it's not an easy problem. So first of all, as I told before, p is unknown. So we can't even define this quantity or can't even compute it. So this is already a big problem. And the only thing we can do instead is to use our training data to measure at least the agreement of our classifier with this training data, which is called usually the empirical risk or empirical error. And this is nothing but the empirical average or empirical expectation of the error function, this indicator function, computed on our sample. So we just count how many mistakes we make on our sample. We divide this by n, the sample size, and this gives us a number, and this is called the empirical error. And of course, it's a good idea to have a small empirical error, or to find a function g which has a small empirical error. And usually we hope that when this empirical error is small, then the true risk or expected risk will be also small. And the whole goal of this statistical learning theory is to quantify how much how wrong we are in assuming that when this empirical risk will be small, the true risk will also be small. And for that, the theory aims at producing bounds, which are statements that tell you how far you are when you think that your true error is small because your empirical error is small. So again, some notation that I introduce here. So we have this training data, x1, y1 to xn, yn, and we produce a function gn. So whenever I put a small subscript n here, it means a quantity that depends on the data that we have determined after seeing the data. So gn means the classifier that we constructed after we have seen the data. So we produce this classifier gn, and the question is, how can we estimate the risk of this classifier? And of course, and that's why this n here, why I put this n here in order not to forget that. This is a random quantity because it depends on the data, and our basic assumption is that this data is a random sample from a distribution. So we need what are called probabilistic bounds. We cannot make any absolute statements. We can only say that because of this model that we have, because we assume that the data is sampled IID from a certain distribution which never changes, then there is some chance, some probability that what we observe on the data will be close to what we would observe if we had infinite amount of data. And that's what is called probabilistic bounds. And of course, you already have seen some probabilistic bounds in John's lecture, and maybe all this is clear to you, but I want to reset the setting. Okay, so there are two main types of probabilistic bounds that we can derive. The first type is of the following form. We upper bound. So all this is with a certain probability. So with a high probability on the random sampling of the sample, we provide an upper bound on the true risk R of Gn, of our classifier that we constructed from the data here, from the empirical error of this same classifier, plus some quantity which is actually the bound, which is this B here. And this tells that the true error can be as big as the empirical error plus some penalty. And this type of bound allows us to estimate from above the true risk from an empirical version of this risk. The other type of bound also gives an estimate from above of the true risk, but from other quantities, usually non-empirical quantities. So there are two types. The first type is you compare the true risk to the risk of the best classifier in a given class. And the second type is that you compare the true risk of your constructed classifier to the best of all classifiers, which is called the Base Classifier usually. And this R star means the best risk you could obtain from a function from x to y. So you just construct the best function, and this best function usually is the function that predicts +1 when the probability of being of y. Okay, maybe I should write it, but I don't know if it will be seeable from everywhere. So again, we have this probability distribution xy. If we look at the probability of y being equals to 1 given x, so at a specific location in our input space, we look at what is the probability that at this location y is equal to 1. So what is the probability that the label of this point is equal to 1? And we look at whether this probability is larger or not than 1/2, then this gives us what is called the Base Classifier, which means whenever this is true, whenever this probability is larger than 1/2, we predict with 1, and whenever it's less than 1/2, we predict with -1. And this is the optimal thing that we could do with a deterministic function. And the risk of this classifier is this R star here. And of course, it's interesting to know if you can provide such a bound, then it tells you, okay, you have built a classifier from the data, and you're that far from doing the best thing you could do. So this provides us theoretical guarantees on the algorithm that we construct. Okay, so again, notation. It's a bit confusing maybe. But okay, the goal is to simplify things. So we have these two variables, x and y, and we just call this pair z. Okay? Now, there are two concepts that I will go back and forth from. The first one is called a hypothesis class, or function class, or classifier class, whatever. And it's the set of all possible classifiers that we consider when we construct a given algorithm. And it contains functions that map the input space to, okay, usually +1 or -1, but it could be more general. It could map to any real number. Okay, so whenever I write G, it means a classifier, a function that predicts some value for all inputs. And when I write F, then it's not the function that predicts, but the function that computes the error of a given classifier. So the way you construct these functions f is that so f is defined on the pair xy, and it computes the error of the classifier g on the pair xy. It compares g of x and y, and it puts that into this L, which is a loss function, which in our case so far is the indicator of that g of x is different from y. And this gives us a number, and this is the value that we assign to f of z. Okay, so we have two ways of looking at the same thing. Either we look at the classifier and look at the predictions made by this classifier, that's g and g of x, or we look at the error made by this classifier, which means we look at the pair xy, we predict with g of x, and we compare g of x with y, and that's f of z, or f of xy. And okay, there is another way, which is we can even look not directly at the error of the classifier, but at the error of the classifier compared to the error of the best classifier, and that's the relative loss, which is written here. It's the difference between the loss, of our classifier minus the loss of the best classifier. Oh, what happens? Sorry. Okay, and why do I do all this? The main reason is that it allows me to treat everything as expectations. Recall that I told you that the error of a classifier is just the expectation of the loss function or the indicator function that it makes a mistake. So now that I have introduced this notation f, I can rewrite the risk of a given classifier g as the expected value of the corresponding f. Right? And same thing for the empirical risk, Rn of g, it's the empirical average of f of z. And to denote expectations, I use p of f. So pf means expectation with respect to p of the function f. And pnf means expectation computed on the sample, so empirical average. Okay, so that allows me to have a somehow simpler notation in the rest. Okay, so now that I've introduced all this notation, and I hope it's more or less clear, let's get to the topic. So if there is anything that you should recall from this lecture, is what is written on this slide. I will detail this in the remaining of the lecture, but I want to give you a first overview of that. So there are two main ingredients when you build a bound. The first one is a deviation inequality, which tells you how far can be a random quantity from its expectation. And you have probably seen many of those in John's lectures, which are called usually concentration inequalities. And the other ingredient is what is called a union bound, and it allows you to treat not just one random variable at a time, but a collection of random variables. So you have these two things. You first have to say, well, for each of my random variables, there is such and such a probability that it deviates from its expectation. But then when you look at many random variables at the same time, for example, when you look at all the functions that you have in your function class, then you need to be able to say something about collectively all these random variables. And that's what is a union bound. And the optimal way of performing such a union bound, so performing a union bound means telling something about a collection of random variables from a statement on each of the random variables. So the optimal way of doing this is by using the metric structure of your space of random variables. And then I will explain what this means in more detail later. But that's the idea. So when you have several random variables, the main thing that you have to look at is how they are structured and how they relate to each other. And once you know how they relate to each other, then you can say something about their global behavior. Another thing which is quite interesting and that you have to recall is that it is possible to introduce what is called a prior, but it's quite different from what Bayesians would call a prior. It's mostly a technical tool. But you can introduce a prior into a union bound, and you can actually tweak the union bound in certain ways according to what you think is more likely to happen when you have data. And the last thing is that the last thing that you have to recall from this lecture is that there is this so-called packed Bayesian technique that I will present, and the main aspect of this packed Bayesian technique is that it allows you to improve the union bound when you average over several classifiers. Okay, and this will be clear in a minute. Okay, so let's start again with deviation inequalities. So this is the most straightforward inequality, I would say. Okay, the notation may not be familiar to you, especially that it's quite different from John's notation, but I will try to explain. So what it tells you is that the expectation of a function minus the empirical expectation of a function is upper bounded by such a quantity here. And okay, you should recall that P of f is nothing but the risk of a certain classifier, and Pn of f is the empirical risk. So this bound tells you what is the difference between the true and empirical risk of a given classifier. And what it tells you is that with a high probability, delta is usually a small quantity, this difference is bounded by a certain constant times square root of this log 1 over delta divided by n. So essentially 1 over square root of n. So that's one thing that you should always have in mind when you look at an empirical average and you want to compare it with the true average for a fixed function, f. This is fixed. This quantity, when the function is bounded, at least, this quantity is of order 1 over square root of n. Okay, that's easy, straightforward, and always true. So with high probability, the difference between those two quantities is of order 1 over square root of n. So that's called Havden inequality, and I should have written somewhere that it requires boundedness of the function. So now, this is fine for one function, but usually you have many functions to choose from. Your algorithm is not restricted to always use the same classifier. At each time, every time it sees new data, it is allowed to pick a different function. So you usually have a set of possible functions, and your classifier looks at the data, tries to find the best one in this set with respect to the empirical error. So the first thing we can assume is, let's see what happens when the set of functions we have is finite. So assume you have a classifier that just has a finite set of functions and picks one from them, from this set. Then you need a statement that somehow is the uniform equivalent of Havden inequality, because you know that for each individual function, you know how to bound the difference between true and empirical risk, but this bound is probabilistic, which means that for certain samples, this will be true, but for other samples, it won't be true, because only for a fraction 1 minus delta of them, it's true. So now if you look at other functions, maybe if you look at, so this is f, let's say we look at f prime, maybe for f prime, the difference is less than 1 over square root of n for some samples and bigger for other samples, but the samples on which it is small may not be the same than for f. So for each different function in your class, you may have different samples for which this bound is valid and different samples for which it is not valid. And so you don't know how many in the end are such that all the functions are within that range. Okay, so that's why you need to perform this union bound. And I've not detailed the way to do it because I thought John did, but maybe not. Maybe I can write it quickly. I think there was something about this, but maybe not written in this form in his slides. Okay, but anyway. So we start with Havden's inequality that tells us that for a given function, the probability under the sampling that the difference between PF and PNF, okay, so it's a bit misleading because this is a probability, so maybe I should write with 2 bars here, and this is the expectation of F. So the probability that the true expectation minus the empirical expectation being larger than square root log 1 over delta over n with some constant, this is less than delta. Okay, so that's one way of writing Havden inequality. The probability that the deviation is large is small. So now you can write this for several different functions. So you write it for, so this is f1, say, and then you write it for f2 less than delta, and so on. And then you want to say something about the probability that, okay, so the bound we want is something that tells us, that gives us a guarantee for all functions simultaneously. So we want to say that for all functions, the difference will be small. So we have to bound the probability that this difference will be large. So which means that the probability that there exists one function for which the difference will be large. Right? It's the opposite thing that we want to quantify. And now we know how to bound each individual probability, and we just have to say what is the probability that one of these events will be realized. So one of these functions will deviate more than a certain quantity, which means we have to bound the probability of the disjunctions of the events, A or B. And probability that of A or B is upper bounded by the probability of A plus probability of B. Right? That's basic knowledge of probability. So if we apply this to this case, then the probability that either function 1 has a large deviation or function 2 has a large deviation is less than the sum of the two probabilities, which is 2 delta. Right? So that's how it works. So if you have n functions, then you just have to replace delta by n times delta. And if you do that, and you write the bound in this way, then it tells you that with probability 1 minus delta, for all functions simultaneously in your class F, the deviation between true and empirical error is bounded by this quantity. So actually, I increased delta by factor f, and that gives me this. Or sorry, I should say, okay. If you look at here, the probability will be less than 2 delta, but then you just rename 2 delta into delta, and that corresponds to dividing delta by 2. Okay, well, I just have to write it. Sorry for not being clear here. But in the end, okay, the important thing is that the bound has increased a little bit because you have lost some confidence in a way, because you're looking at many different functions at the same time, and any of them could deviate. So the bound is a bit worse. And how much worse is it? It's worse by this log of size of the class of function term. And you can think of this term as a variance. In a way, the more functions you have, the more variability you have, because not only can the empirical average deviate from the true average, but also you can choose different functions. So this adds some variability to your random quantity. And another way to think of this log of size of function class is as a measure of the function class, a measure with respect to random fluctuation of a quantity. And you have seen in John's lectures many other measures of size of a function class, the VC dimension, or probably you've seen covering numbers, the fat shattering dimension, and Radmacher averages. So all these quantities are quantities that measure the size of a function class, and the log of number of functions is the most basic one. Okay, so this is for the union bound. I don't know, is it clear for everybody? Are there any difficulties here?
C instead of big O?
No, C means a constant here. Yeah, okay, you could, yeah. But this is true for each n. Big O would be somehow in the limit. So this is true for each possible value of n. And yeah, and the constant here does not depend on anything. It doesn't depend on the size of the class of function. It doesn't depend on delta, and it doesn't depend on n. Okay. And usually, okay, in this specific case, it's something like 2. But it depends on the bound that you have on your class of function. But usually the loss is between 0 and 1, and then C is something like 2. Okay, so the next thing you can do, and that I'm pretty sure that was mentioned at least in John's lecture, is that you can somehow weight all your function in a different way when you perform the union bound. So here I had written the same bound for each function, but I can slightly modify the bound that I write for each function, and especially I can have a different delta for each such bound. So I can write here delta 1 and here delta 2, and then I can just do the same thing, the same union bound, and what I get is that now my delta depends on the function. And it depends in the following way. Essentially, we have to make sure that all these deltas that we write here, when we sum them up, we have something which is still small, which is still a delta. So we just have to make sure that delta 1 plus delta 2 equals delta, for example. Right? So we just pick two numbers, delta 1 and delta 2, such that their sum is equal to delta, and then we can do the same thing and get the bound that tells you that with probability 1 minus delta, we have this, at most, this deviation. And, okay, here that would be a log 1 over delta 1 or log 1 over delta 2, depending on the function, and I just written this, I just separated the term pi of f from the delta. So, and that's not clear again, because I skipped a lot of details. Essentially, the easiest way to have a sum of deltas that is equal to delta is to take a probability distribution over your class of functions. So for each function, you have a number, pi of f, such that the sum of this pi of f, this number is non-negative, and the sum of this pi of f is equal to 1. So that's a probability distribution on your class of function. Okay? And once you have this, you just write the Havden bound for each function with delta times pi of f. And when you will sum all these things, then you will get delta. That's the trick. And that's why you get log of 1 over pi of f here. And in the simple case, where you put equal weight to all functions, pi of f is 1 over the number of functions, so log 1 over pi of f is just log of the number of functions. And you recover the previous bound. But you could imagine to put a different weight on different functions, and then you would get a different bound. And that's a bit surprising, because you can say, well, what if I put all the weight on one specific function? Then I get a bound which is as good as the Havden bound. But the problem is, and that's where there is a trick, this specific probability distribution pi of f has to be chosen before you see the data. So it cannot be a random distribution here. So even if you knew in advance, even if you guess in advance what will be the classifier picked by your algorithm, and you you can guess before seeing the data what will be the classifier picked by your algorithm, and in that case you could put all the probability mass on this classifier, and then you get a super good bound. But in general, you don't know beforehand. Before seeing the data, you don't know whether the hyperplane will be like this or like this. Right? So that's why you cannot really hope to improve your bound by picking the right distribution. But still you can hope to do something, because you can have an idea about how your algorithm sorry, about how your algorithm will behave. For example, you know that in general your algorithm tries to minimize the empirical error, so it will try to find functions that have low empirical error, or you know that it maximizes the margin, so you know that you can put more weight on the functions that have a large margin because those are more likely to be chosen by your algorithm. And if you do that, you put more weight on these functions, then you decrease the log 1 over pi term, so you get a better bounds for those functions. So you can imagine to put here something that would be proportional to the margin, and then you get a bound that tells you, well, whenever the margin is large, then the bound is small. And why? Because I assume that the algorithm will pick functions with large margin. But of course, if it happens that when I train my classifier on my data, I get a small margin, then the bound is bad. So it's just a bet that you make before running your classifier, your algorithm. You just bet that the classifier will have such a margin. And if you bet, I mean, if you're successful, then you have a good bound, and if you're not, then the bound is worse. So you cannot hope to have always a good bound.
Can you take any probability distribution and then the margin, for example? You just choose one. You have a
Yeah. I mean, there is no restriction. Okay, here the thing is, if you have, I mean, this only works, for example, if you have a countable class of functions, because otherwise your let's say the probability of a single function is 0 always when you have a continuous distribution. So this log 1 over pi blows up, and you have a bound that is useless. But at least if you have a countable class of function, you can take any probability distribution. But most often it's hard to define such a probability distribution. Okay, so this again summarizes these considerations. So pi here is not, I mean, it's different from a Bayesian prior in the sense that it's not that we hope that our function is chosen from a probability distribution pi by some device, but we just make a bet. We just say, okay, let's pick some distribution, and if we are lucky, then our bound will be good, and if not, then it will be bad. But it has nothing to do with the process of generating the data or generating the function itself. And okay, so if you want to have a good bound, so what would be the ideal probability distribution or ideal weighting? The ideal weighting is such that each function is assigned a weight that corresponds to how likely it is to be chosen by your algorithm on the specific data that you have. So if you were able to sample repeatedly the data, train your classifier, look at the function that is chosen, and if you were able to do this many times, then you would obtain the ideal or optimal probability distribution pi. But of course, again, it's not possible to do this. That's why you somehow have to guess this pi beforehand. Okay, so as expected, it's a bit slower than I thought. So maybe I'll skip that. I think maybe I'll come back in the next lecture on this topic. So here are other ways in which we can improve the union bound. So the first, I recall, the first step was finite union bound, just log of the number of functions. The second step is to introduce these weights, and we get log 1 over the weight. Then another thing you can do is to use the symmetrization trick, and that was explained by John, I'm pretty sure. Okay, so when you do that, the idea is that you introduce another set of data. So this is the ghost sample, and you look at your functions class on this double sample, on the initial sample and on the ghost sample. And you just have to count how many functions you have when you look at them through projecting on this sample. And actually, you can just perform a union bound on this restricted set that you obtain. And that's why you obtain here, instead of the number of functions in your function class f, you obtain this Sn, which is the size, you obtain the cardinal of this set Sn, which is the functions projected on your Gauss sample. Okay, so that's also one way to improve the union bound. But the problem is now that your set is this set of functions here, or this set of vectors, I should say, is something that has to be computed from the Gauss sample, and this Gauss sample does not exist, right? That's why it's called Gauss. It's just something, a mathematical device, if you want. So it's not, I mean, you could do something like, I take my training data, I split it into two, and I just train on the first half, and then compute the number of functions with using the second half. But then you don't use all the data for training, and that's not so optimal. So usually what people do is that they upper bound this using data independent quantities like the VC dimension. And it's somehow in the similar, it's the same idea that again you can look at it's enough somehow to look at the function class projected on this Gauss sample. So you could say, well, instead of just doing the simple union bound of counting how many functions I have, I can be a bit more clever and introduce these weights again. So you can introduce a weighting function, this big pi here, that weights each function, and I put z1, zn, and so on to indicate that now this weight is allowed to depend on this double sample. Because of symmetrization. So you can just do the symmetrization proof, and when you do the union bound, introduce the weights, and you will see that the weights can be introduced in such a way that they depend on the data and the Gauss data. So again, if you have a training sample, you split it into two parts. You train on the first part, and then you can say, you can define your weights based on this data. So you have a bit more flexibility here. You don't have to guess everything. You can say, well, given this data, well, I think that given this data, my classifier will choose such and such a function, and this allows you to fine-tune your weight according to your data. So you have a data-dependent weight. But okay, there is a catch, of course. Again, it depends on this double sample, but also it has to depend in an exchangeable way on this double sample. So you could say, well, let's just make it depend on the first half of the Gauss sample, so then it does not depend on the first half of the double sample, so that it doesn't depend on the Gauss sample. But you're not allowed to do this, because for the proof to go through, your weight has to depend on all the samples from Z1 to Zn prime. Otherwise, you're not able to symmetrize things. So it's a bit better, but not fully satisfactory. And usually most approaches that are based on that have many difficulties to relate what happened on the Gauss sample to what happens on the initial sample. So then comes in the other trick, the Rademacher average approach. So this is also something that you have seen before. And using essentially Mach-Dirichlet's inequality, you can show that for all functions, the difference between true and empirical error is bounded by this quantity here, which is called the Rademacher average for the class F, plus some term of order 1 over square root of n. And this is actually not a union bound. I mean, there is no union bound here. It's purely deviation inequality, concentration inequality. So where is the union bound? The union bound comes in when you want to actually compute the Rademacher average, or upper bound the Rademacher average. And again, you can do the same thing. You can, for example, have, in the finite case, a simple-minded union bound that would upper bound this Rademacher term by square root of log of number of functions divided by n. So you would recover the same type of bounds that we had before, but using a slightly different approach. So, but the idea is that when you are at this stage, when you introduce this quantity, it seems that you are done because you have a bound, but most of the work remains to be done in bounding this Rademacher average. Of course, there are situations where it's possible to do it more or less directly, but in most cases, you have to actually do a union bound. And so one way to do this union bound, so is to count the number of functions, but again, if you have infinitely many functions you cannot count, you have first to project. So you can say, I project on the double sample, and now the good thing is, once you are at the Rademacher level, so once you have done this, you already have done symmetrization, and you have gotten rid of the Gauss sample. So if you remember the proof of how to get here, you first have to introduce a Gauss sample and then use the fact that Gauss sample and initial sample can be exchanged, and then you introduce the Rademacher random variable sigma I that are either +1 or -1 depending on whether you leave the samples in the same position or whether you exchange them. And then in the end, you use the fact that the initial sample and the Gauss sample have the same distribution to say that you can cut your Rademacher average into two pieces, and the two pieces have the same distribution, so they are the same. Okay, you can just look at the slides. But the idea is that the good thing about this approach is that you can get rid of the Gauss sample. So then you can do all these tricks again, but without the need for using the Gauss sample. So you can just count the number of functions that you obtain when you project your function class on the sample, and just use this as a bound. Or you can use what are called covering numbers. What does it mean? It means instead of counting how many functions you have, you first create an approximation of your class with finitely many functions, and then you count how many functions you have in this cover. But of course, since you approximate your class, you lose a little bit because you can say something about functions in that cover, but not all functions in your class, and the difference is the size of the approximation. So you pay a little bit for the error of approximation. But then you can say, well, why don't I just approximate again? So you first start with a big cover. So you just pick, say, one function, and you say, I approximate my whole set of functions by one function. And then I can have a very good bound because I just have one function, but I pay a term which corresponds to more or less the radius of my function class. And then at the second level, you say, well, now I will approximate a bit more. I will put 3 functions, say, and then again, I pay a little bit. And you can repeat this procedure of adding more and more functions to approximate your function class. And what you obtain in the end is something that takes into account the number of functions that are needed to approximate your function class up to a certain radius, and that's called the covering number. So n f epsilon dn is the number of functions that you need to approximate your class f at a radius epsilon in the metric dn, which is the metric of the vectors obtained when you project your function class on the data. So before doing all that, because you're in the Rademacher setting, you just project your class of function on your data. You obtain a bunch of vectors which are 0, 1 vectors because it's just the loss that you make on each data. And all these vectors, you look at how they are spread in terms of the metric which correspond to just the Euclidean metric between vectors. No, it's not necessary. Just, I mean, it's basically a metric space problem. So you have a space of functions. You project that. You obtain a set of vectors. And now this set of vectors is a metric space endowed with the standard Euclidean distance. And you try to to compute the size of approximation to this metric space that you can construct with finite vectors, finite number of vectors. And this is this term here, and you just have to integrate it, which corresponds to the idea that you look at all possible levels of approximation. Yes?
You know that the covering exists because you project in this finite dimensional space.
Yes, but right. You can.
It depends on the data, and that's why you did the interpretation.
Yes, exactly. But that's an interesting question because, of course, you cannot always approximate an infinite set of functions by finitely many functions, especially when you want to approximate very small. But this quantity here, the integral of this log, may still converge. Because the problem is when epsilon gets small, then this number may blow up. But as long as it doesn't increase too fast, then you can still compute this integral. And for example, if you have a finite dimensional space, the number of balls that you need to cover a space of dimension d at radius epsilon is proportional to 1 over epsilon power d, right? So this goes to infinity very fast when epsilon goes to 0, but still you can, if you compute this integral, then it's finite. And you can have much bigger spaces than this. You can have infinite dimensional spaces and still have convergence of this integral. So as long as the covering numbers do not grow more than exponentially, then it's fine. Oh, sorry, the log of the covering number do not grow more than exponentially. Okay, and this is called somehow the global metric structure that you're capturing via these covering numbers. And I'm a bit over time, so I will finish soon. Sorry. And there is a way to do something a bit more clever by, instead of looking at covers of your space of functions that are global, which means global in the sense that everywhere you want to approximate at a certain accuracy, you can do things a bit more local, and there is actually a quantity which is called majorizing measure bound, which is written here. It's not very easy to explain, but let me just say that the idea is to, instead of covering your space, you construct a partition of your space into finer and finer partitions, and you ensure that your partitions have a certain diameter. So again, it's the idea of balls. You can think of balls as a partition if you want. But in addition, you put weights on this partition. So again, this idea of weighting comes in, and that's why there is this pi here. So you put a probability distribution on your space of function, and that gives a weight to each element of the partition. And by computing this quantity, you have something that estimates the Radmacher average, and that actually, if you choose these weights properly, is equal up to a constant to the Radmacher average, which was not the case of this quantity here, which is covering numbers. So using covering numbers, you can upper bound the Radmacher average, but you lose something. Whereas if you introduce weights in addition to your to doing this covering, you can match the value of the Radmacher average. So this is somehow the optimal way of performing this union bound. And now I conclude with these take-home messages again. So as I said in the beginning, we have these two ingredients in the bound, the deviation and the union bound. This lecture was about the union bound. Next lecture will be about the deviations. The optimal way of performing the union bound is to take into account the metric structure of your space of functions after projecting on the data. And that's called generic chaining. I did not mention it, but that was the title of the slide. You can introduce a prior into the bound, and that's this weighting pi, and that allows to improve the union bound. And the best prior, as I said before, depends on the algorithm, and ideally you would like to estimate beforehand what the function, which function will be chosen by the algorithm. And I did not talk about the packed Bayesian technique, so I will not come back to this. So maybe in the next lecture. Thank you.